Hello everybody, welcome in my third episode on my tutorial series on STM32 programming. Today's topic is the setup of the ADC single channel. The goal is that I want to use the ADC for measuring the voltage on my trim pot. The voltage will be varied from 0 to 3.3 volts. The first way to set up the ADC for a single channel is to set it up as a single conversion in the software trigger. In the software, we have to poll for every conversion of the ADC. This is the most simple method for setting up, but also it is the most demanding method for the CPU. At first, the polling program will eat some of your memory, and also it eats some of your clock cycles, which slows down the main program. The second method is continuous conversion and software trigger. This is quite dangerous method and shouldn't be used that often, because when you start converting with the continuous conversion mode, the ADC will convert the values at the maximum clock speed of the ADC. We usually use this method by short bursts when you set the ADC on and off, and in the short interval it will do a lot of conversions. The same as the previous method. This method by software triggering is more demanding on your code and CPU. The third method is single conversion and a hardware trigger. This is quite more difficult method to set up, but it is very rewarding. You have to use a peripheral, for example a timer or an external interrupt, to start the ADC conversion. By using the interrupts, you can save a lot of clock cycles and memory. The next method is ADC continuous conversion mode with hardware trigger. The same as the previous method, it uses hardware interrupts, for example timer or external interrupt, to start the conversion. But again, this mode should be carefully used for the specific applications. The last two methods are ADC DMA one-shot mode and DMA circular mode. About DMA I will talk in the later videos, so for now let's ignore these two possibilities. For every option it is possible to use single channel or multi-channel conversions, but for certain options the setup is easier and more practically acceptable. So without further delays, I will go straight to our IDE and start coding. For the project setup and clock setup, look at the GPIO or external interrupt video. I will use the frequency of 48 MHz. Okay, so here's our main. Well, before we start to set up the ADC, I will show you something important in the datasheet. Here is the datasheet. You will find chapter functional overview, and you will find ADC over here. The important thing I want to show you is over here. Some of the external channels are shared between ADC 1 and 2 and between ADC 3 and 4. Now we know that some input channels are actually shared between ADC 1 and 2. I want to use ADC channel 1 for ADC 1. So let's look in the pin overview. We'll close this chapter, open chapter pin out and pin description. Over here, pin definitions, and if I will scroll down, here for example we can see ADC 1, 2, input 10. This 1, 2 doesn't mean ADC 12, it means that it's ADC 1 or ADC 2. For example, this is the shared channel, and I want input 1. So let's scroll down. For example, over here is just ADC 1, which means this channel is not shared. This is exclusively for ADC 1. Also important thing is I have socket 64 pin socket, so we must make sure that actually our microcontroller has available these pins. ADC channel here. ADC 1, input 1. Okay, so we see that channel 1 is actually not shared between ADC 1 and 2. And we can see that it is on port 8, pin 0. When we know which port and pin we can use, let's go back to our IDE and let's start setting up our ADC. As an ADC setup, I want to use hardware trigger and a single conversion method. I will do it like this because if you can understand how to set up the ADC the way I will show you, setting up the ADC via, for example, software trigger will be no problem for you because it is much easier, but as I said, it's least efficient. For the configuration process, we need to use delay. So we can go, for example, for our GPIO tutorial folder and copy it from there. GPIO tutorial or source main.c. I will actually copy both of these defines. These are also useful. We need this variable timing delay, this private function prototype. Let's scroll down, and we need both the sysdig handler and a delay function. And let's copy it between these two commands. Use the code begin for. Also, let's not forget that we must delete the sysdig handler definition in an interrupt folder. Let's close this. Let's find our tutorial ADC, core, source, F3XX interrupt. Let's delete. Save. I will now describe you how I want my program to work. I want to configure the ADC to trigger on some sort of interrupt event and to do a single conversion. I want the interrupt event to occur every second. For this, I will use a timer. The ADC will be configured that it will start a conversion only on a rising edge. So the timer every 1 second will generate a rising edge, and therefore the ADC will know that it must do a conversion. Also, to make it easier to see that my program works, I want to toggle an LED in each interrupt event. The LED configuration I can copy, for example, from the GPIO tutorial project. So it's over here. I will toggle both LEDs at once. I will copy it into our main over here. And actually, I can also configure the sysdig timer. Right, like this. Okay. Okay, now we can close this main.c from our previous project. And let's start to write a brand new code. This code will be quite longer. It is quite difficult to properly configure the ADC. At first, we must configure our GPIO. We know that we will use port A and pin 0. So at first, we can basically copy this RCC peripheral clock enable and write over here A. And the next thing we need to do is to set the mode of the GPIO. And To set up the analog mode, we need to write both motor bits to 1. We actually right now don't need to null the bits. Okay, and we write 1 1 to 0 and 1 bit. I can actually leave it, I could leave it like this, but to make it more proper, I will null the rests. The next thing we have to do is to set up the clock for the ADC peripheral. For this, let's go to the reference manual. ADC, functional descriptions, clocks. And over here we can see that we can either use specific clock source, which is an independent and asynchronous with the advanced high performance bus clock, or we can use as the ADC clock that we will derive it from the advanced high performance bus clock, and we will use some sort of prescaler divider. To use the option 1, we must set the bits of the CK mode reset, and to use the second option, we must set up the CK mode different from 00. For my implementation, I will use the first option. So let's look at the register and set up the CK mode to 00. Okay, close this chapter. And the important thing is that it's actually in common control register, which is shared between the ADC1 and ADC2. Even though our channel is specifically only for the ADC1, to set up the clock for the ADC1, we have to go to the shared common register. Here you can see on bit 1716 is the CK mode. And over here we can see 00, asynchronous clock mode, generated at product level referred to the RCC. And over here we can see the prescalers for the second option. So let's write it. It is ADC 1 to common. It's very well hidden, so it is named like this. We will go to the, actually I need to look again, CCR, and we are resetting the both bits. CCR, CK mode. Okay, so we are writing 1-1 on position 16. Okay, that is correct. Then we are nulling it and putting it into the register, so perfect. So the reference manual told us that if we want to use this clock, we need to go to the RCC for further setup. So let's go. Let's close this chapter. I'll actually open it once more. Okay, so we can configure it in the RCC to deliver up to 72 MHz, which is basically PPL output. But also, we will be capable to use the prescaler over here. Option A, we can, basically the advantage is we can use the maximum clock frequency. We have quite a lot of options to divide it by this prescaler. So let's go to the RCC chapter. And let's find our prescaler. And it's over here. ADC 12 prescaler. Bits from 4 to 8. And I actually want our PPL clock to divide, for example, by 2. Okay, so let's go to our RCC. It's configure register 2. We are actually setting bits. RCC configure 2, and here it is ADC prescaler 12, and I want to divide it by 2, so let's use this CMSys macro. And it is in hexadecimal 110. To make sure that the value is correct, I will actually check it. You can go, for example, on this website, and here we will have 100, 110, and it is 10010000. We know that it is nulled bit, first bit, second bit, third bit, fourth bit. That's 1. Fifth bit, sixth bit, seventh bit, and 8th bit. So on 8 and 4 we have 1. Let's go to the reference manual. 8, 4 is 1. 8, 4, 1 divided by 2. Perfect. So now we just need to enable our ADC clock in RCC. Let's go again to the reference manual. And let's actually look in which clock register we can enable the ADC. Okay, so it's this register, 28-bit, perfect. To show more properly what I've done, I can actually go to MX, go to clock configuration, and if I could find, and over here we can see, can I zoom it? Yes, I can. That here I have 48 megahertz. This is our 8 megahertz multiplied by 6. Here is 48. And I have set actually this prescaler to 2. Over here you can see that I cannot click on it. You cannot set it inside. You have to set it in your code. So in our ADC 1R2, we will have 24 megahertz. We don't need that much of a speed. The next step is to start the ADC configuration itself. Let's go into our reference manual and let's look what the reference manual is saying. ADC, functional description. I will go right to the voltage regulator. The sequence below is required to start ADC operations. Enable the ADC internal voltage regulator. The software must wait for the startup time of the ADC voltage regulator before launching a calibration or enabling the ADC. This must be implemented by software, by us, and the startup time is equal to 10 microseconds in the worst case. Okay, and now in the enable sequence, we see that the first step is to move the bits from 1, 2 into 0, 0. So we need to put both bits into reset state, and then we have to write it to 0, 1, which is enable state. So let's go and find it in the registers. Yeah, it's over here in the control register, voltage regulator enabled. So in the reset state, when we power up the MCU, it will be in 1, 0 position, 1, 0 value, and we need to at first reset it and then set it to 0, 1. It is the intermediate state. It is written that before we set it to 0, 1, we have to actually reset it. So let's do it. ADC 1, control register. It's only ADC without any number, because we are writing to a specific ADC, not to a common register. And here is voltage regulator. And we need to set both bits to 0. We need to set it set the 0 bit to 1. Now the reference manual told us that in worst case scenario, the regulator, it takes the 10 microseconds to set up. I have a millisecond delay, so I will just keep it 1 millisecond. 1. Like this. Now let's move again to the reference manual and look what do we have to do next. we have been this chapter, so we need to move straight to the calibration process. And over here we can read that the calibration is initialized by software by setting the AD cal to 1. Calibration can be only initiated when the ADC is disabled. AD enable 0. ADC calibration bit stays 1 during all the calibration sequence, and it is then cleared by hardware as soon as the calibration completes. Also, the calibration factor can be applied to single-ended input conversion or the differential input conversion. I will use a single-ended, so I will write ADC calibration differential to 0. Let's go to the IDE and let's write it. So let's continue in our calibration process. We are nulling. And we are nulling AD enable. Leave. Now let's set the ADC calibration bit over here. And now we cannot continue until hardware sets the calibration bit back to 0. Otherwise the calibration is not complete and the ADC would be inaccurate. To make sure we will not, the code will not continue, basically we will do like that the control register and this bit, if it's not equal 0, remain in this empty while loop. And while the calibration is not complete and therefore the calibration bit is still 1, the MCU will stuck in this while loop. We can also get the calibration factor. For this, I have already off screen set it up this unsigned integer called calibration value, and to get the calibration factor we basically know that it's in this register calibration factor. I will show you just in the reference manual that I'm not making this up and it really exists. Over here. This is for differential mode, this upper one, and the lower one is for single-ended mode. These bits are written by hardware or by software because we can also manually set the calibration factor, but for now I don't see any reason to do it. Okay, and now we will continue to ADC Configuration. We will be moving in the configuration register, which is over here. And here I will already point out some of the important parts of the register. The first is bit 13, single on continuous conversion mode. This bit, as you can see, is actually not resetted when you reboot the MCU. So for example, if in the previous application you've used continuous mode, in the next calibration, if you want to use a single-ended mode, you actually need to rewrite it back to 0. Over here, next important is extern. External trigger enable and polarity selection for regular channels. We are using a hardware trigger. I will use a timer, I will configure it later, but for now I want to ADC to start converting on a rising edge, so we must set up 0 and 1 for the hardware trigger detection on the rising edge. And here is external trigger selection for regular loop. These bits select the external event used by a trigger and start the conversion of the regular group. These are several timers and external interrupts. I can actually show you. It's very important. Because from this, we then must choose the hardware peripheral which we will use. And over here are the numbers from 0 to 15, and we can see timer 1, capture compare, CC1, CC1. So, and for example, I want to use timer 15 because for me personally is the least used timer I use usually, and I think everybody usually use timer 1, 2, 3. He probably doesn't go and, oh, timer 15, let's use this. So I will use this, and here is trigger output event. So when the timer with each tick, with each rising edge, it will generate a trigger output event. So this is important because we can set the timer to do, for example, capture compare event or something like that. So this is telling us that if you want to use timer 15 on the channel 14, we must use trigger output event. Also, here we can see, for example, external interrupt line 11. So we can start the ADC conversions manually, for example, with some kind of moving part, for example, encoder or button, depends. Okay, let's go back to the ADC configuration register. And let's go further. So data alignment. This is how do we want to align the data. I want to use just a regular light alignment. If you are from Arabic country, you can use left alignment. Data resolution. This is actually quite important, depends what is the resolution you want your ADC to work with. But watch out, with increasing resolution, you need more clock cycles to do a proper conversion. Makes sense. I want to use the 12-bit resolution, which means we will get 4096 values, which we can then convert or recalculate into voltage. And here are just DMA. Okay, so let's start configuring. It is configure, and we will at first null the continuous conversion mode. Then I will null align mode because I want right alignment. And resolution. Over here. Okay. The next thing we now do is to null the external trigger enable because, for example, from previous application, we can have the interrupt trigger selected to, for example, some event or falling edge. And we want it to trigger the interrupt on the rising edge. Trigger the interrupt on the rising edge. We must write 0, 1. So the nullth bit next thing we must do is to select the channel itself, event, and we know it's event 14, and 14 in binary is 1110, so it's 2 plus 4 is 6 plus 8 is 14, and we will get event 14. So we will be setting will be 1, 2, and 3. Now the ADC still don't know which channel to convert. We know that we want to convert channel 1 of ADC 1. So let's look into the reference manual, and about the conversion itself, we will go over here in channel selection. Here we can see some additional information about the channels itself, what they are connected to. For example, there is some temperature sensors, battery measuring challenge. And this is important. It is possible to organize the conversions into 2 groups, regular or injected. Group consists of sequence of conversions that can be done on any channel in any order. So we can, for example, convert channel 3, 8, 2, 2, 0, 2, 2, 15, end of sequence. Regular group, it is composed up to 16 conversions. I will use the regular group. I will not do the injected group. And why I'm still in the reference manual? If you remember when I talked about the ADC resolution, that with increased resolution you need more clock cycles to properly do the conversion. I will use 601.5 ADC clock cycles, and here is the conversion type. So sample, it is 601 plus 12 plus 5, and here is the last important thing, is the single conversion mode. And over here at the nodes, to convert a single channel, program a sequence with the length of 1. So even if you are converting just only one channel, you have to still define it as a sequence with the length of 1. So let's look into the SQR register. SQR1, regular sequence register. I will start from the bottom, and here you can set the length. You can see that 0000, one conversion, and here is the first conversion of the regular sequence, and you have to write the number of channel. And it is actually in every node that there is the channel 0 is not mapped, it doesn't exist, so all zeros should not be used. So we are using channel 1, so we will write this register 0000 in the L bit length and 00001 into the first conversion in the regular sequence. And because the length of conversion is set to 1, and we just need to program only the very first conversion in the regular sequence. So let's write it down. ADC1 sequence, and we are at first writing SQO1. We actually can null it. So now we've set that the length of the conversion will be just 1, the length of the sequence. And now just write the 0th bit. And now what we did is that I can at first actually null it. So at first I nulled the registers in the first channel of the conversion sequence, and now I just wrote 1 on the 6th position. It's in hexadecimal, but it doesn't matter because it's still only 1. And here is the 6th position, so it's 00001. So the channel 1 will be converted all the time. Now let's set the sample rate. We already know that we want to use the slowest sample rate. I will set this. I will write number 7 on position 3, and I will show you here in the reference manual. It is ADC sample time register. You can see that for each channel we can set a different sample rate. This is very good because, for example, for STM32 series, you have one shared sample rate for all the ADC channels. So if you have, for example, 2 ADCs or just one ADC on these small microcontrollers, you can set only one sample rate. And here it is 111, which is 7 on position 3, 7 on position 3. Perfect. Now we have to set the end of conversion interrupt. If we would use multiple channels, we would have to use also the end of sequence interrupt. For this, I will go to the reference manual and I will show you why it's necessary. Single conversion mode. And at first we've already over here inside the regular sequence, after each conversion is complete, the converted data are stored in 16-bit ADC data register, and we have to set the ADC end of conversion, and an interrupt is generated if the end of conversion interrupt enable is set. So every time the channel completes its conversion, the end of conversion interrupt will be set, and we will read the data value stored in this register. So now let's look into the register itself. It will be ISR, no, sorry, interrupt enable register. Here we can see end of conversion interrupt enable for a regular sequence. That's just over here. End of conversion interrupt enable. We must write it to 1, so ADC1 interrupt enable register. And of conversion. Okay. And now we have to set the priority and enable the interrupt in the nested vector interrupt controller. Enable and set priority. No, I hope that I remember. Yeah, I think it's this one. I just make sure that it's really correct. Vector ADC1 and ADC2 interrupts. Okay. So here you can see that actually ADC1 and ADC2 shares the interrupt vector. So this both ADCs are not as independent as they seem. I can just copy this and I want priority 0. Now I will show you in the reference manual how to enable the ADC. Over here, the on and off control, and here is software procedure. Set AD enable to 1. Wait until the AD ready is 1. And here there is a note that AD enable bit cannot be set during AD calibration and the 4 clock cycle after that. Now let's write the code. I will actually put it into do while loop. I will explain why. AD enable. So now I wrote that I've set basically the AD enable bit, but let's look where the AD ready actually is. And I know it's an interrupt vector, but it's basically just an interrupt. ISR. And here on the 0th bit is AD ready. And until it's not 1, the ADC is not ready to start the conversion. So let's put in the while loop. R and AD ready until the ISR and AD ready is equal 0, remain in the do while loop. You may ask, why did I use do while loop? It is because it saves clock cycles, and usually during a configuration or startup or something like that, the programmers use the do while because it at first executes the code inside do brackets, and then it checks if the statement or the condition is true, and if it is, it already can escape and continue in a program. If I had just while loop, the program would at first check the condition, then it would set the AD enable bit, and then it have to again check the condition if it's correct. That's why I used this. Now I have to configure timer 15. Okay, at first we must set up the peripheral clock, but we must know that to which peripheral clock the timer 15 peripheral is connected. For this we can go to the clock configuration in the MX window. Okay, over here we can see that currently the timer 15 is connected to the peripheral clock 2. Now let's go to the registers. RCC registers, APB2 peripheral reset register, and we want enable register, and it's over here. APB2 peripheral clock enable register. And over here on bit 16 we can see timer 15 enable. Next thing we must do is to set the timer as a master. Why? Because the ADC will react on the update generation event which will be created by the timer. Therefore, basically the timer is the master and the ADC will be the slave peripheral. For this, I will go to back to registers, timer 15 to timer 17. Again, I highly suggest to read all the information, and here timer 15 registers, and it's in control register 2. And over here, master mode selection. These bits allow to select the information to be sent in master mode to slave timers for synchronization. TRGO. If you remember, TRGO was also in that ADC setup. And we want to create not reset, not enable, not compare pulse, not compare. We want to create update event, trigger output. And it's 0, 1, 0. So let's set it. It's timer 15 CR2. I will at first null all the 3 bits. CR2 master mode selection, and we actually want to set all of them to 1. Okay. Now I want to set the second right. Yeah, it is 1, 4, 5, 6, 0, 1, 0, and I write 2. Oh. It is, yes, this one. Position. It's 2 on position 4, so it's 1 on position 5. 1 on position 5, correct. Okay. Next, we must set the clock prescaler. This is the same for every clock timer. I will use value 999 999, but the final result value is 1000, because in the reference manual you could read that the total prescaler or the total divider value is 1000, because it's 999 plus 1. Next we have to set the auto reload register. As I said earlier, I want to make the trigger output every 1 second, and I have frequency 48 megahertz. Now I divide it by 1000, so it's 48 kilohertz, but I still need to divide it by 48,000 to have 1 second. AIR. Over here, there is nothing difficult, just write 48. Now, let's just enable the timer itself. I will actually show you in the reference menu what I've done. It's over here, the 0-bit counter enable. Bit 1 counter is enabled. And finally, this is all just for setting up the ADC and the timer. Now we just have to start the ADC, because it is configured, it is enabled, the master timer is enabled, but the conversion must start. DC1, and I will actually look in the reference manual, because you need to know where, in which register it is. It's over here in control register, bit number 2. Start of regular conversion, write 1 to start regular conversion. ADC is operating and eventually converting a regular channel, eventually by the timer. CR. ID start. But we are still not done. We need to configure the ADC Interrupt Handler, and also I want to recalculate the measured value to voltage, because we will get a value from 0 to 4095, but it's not equal to the real voltage. So I will show you how to do it. So let's create our interrupt handler. Again, we copy the name of the vector, go over here, and if ADC1 ISR and end of conversion interrupt is not equal 0, do several things. At first, I want to toggle the LEDs to show me that the interrupt is occurring and the code is successfully getting inside the interrupt handler. For this, I will show you another way how to toggle an LED, but I do not recommend it to use it in more robust and complex applications. We'll go to output data register and toggle. This is a toggle sign. and it's output data register 8 and data register 9. I will put it into brackets like this, and then I want to save the value in the ADC data register into some kind of variable. I already know that it's unsigned short. This in a reference manual, and for example, converted value, and then I will make voltage value, and I will also make another variable ticker. C1 data register. That is basically it. Then ticker is equal to 1. And this is the end of our interrupt handler, because we would there are two ways how to escape this interrupt, because for example, you remember, if you are in external interrupt, you need to write 1 to pending register to clear it. And over here we have ADC ISR end of conversion. There are two ways to clear it. One way that you will directly write to it 1, and the second way, and that is what I recommend to use, is when you read a value from the data register, the interrupt will automatically clear itself. This is very well done by the manufacturer. And now I want to recalculate the converted value into real voltage. I will go to while if ticker is equal to 1, voltage value is equals converted value multiplied 3300 divided by 6. This is it. And ticker equals 0. Properly escape this condition. So we multiply the converted value by 3300 and divide it. This is a simple math. Okay, and now it's already it. Let's build the code. And seems like we've got some warnings. One is over here. Oh, of course. We are not assigning, we are just comparing. So over here and over here, be like this. Now it's correct. Okay, so now I will record the results, and then I will move back to a debugger, and I will show you the measured values. Okay, now we have the proof that our program works and our LEDs are successfully toggled inside the interrupt handler. Now let's go to the debugger and see what we actually measuring. So welcome in the debugger. Now I will add this values into watch expression. Okay, pause, and we see that we've got calibration value 65. The reason why we don't see converted value or converted voltage value is because my trim port is turned all the way to the short circuit. So I will turn the trim port into the extreme value, which should be 3.3 volts. And it actually is. It's almost, because it's a hardware mechanical part, you cannot turn it all the way to the max and all the way to the bottom. So this is acceptable. Actually, if I play, so we can see that the ADC has actually some spread of values. I will turn it, for example, in more or less 50%. Why I'm saying more or less? Because my trim port is not very accurate. It has only 180 degrees turn. Yeah, we are more or less in the 50%. You can see that the value jumps a little, but it's okay. You can read potentiometer, things like that. So that's all I wanted to show you today. The program works, ADC works, the LEDs are blinking. Thank you for watching. See you next time. I appreciate your comments and likes. And next time I will write some libraries which will automatically calibrate and configure the ADCs, GPIOs, and external interrupts. So in the next applications, we do not have to write them manually again. Goodbye.